We start this video by solving the linear state equation. The first equation shown on this slide is the SE of a state space representation, and we want to solve for xt. How do we do this? Again, we take the Laplace transform of the state equation so that we have a switch of domain. We switch from the time domain into the Laplace domain. And then the differential equation becomes an algebraic equation. But then we need to take the inverse Laplace transform, so that will bring us back to the time domain. When we take the Laplace transform of the state equation, we need to use the properties of the Laplace transform. The first property we need to use is the derivative law. So that's the left-hand side. And then right-hand side, when we take the Laplace transform, it becomes a lowercase xt becomes capital X, S tilde, because it's a vector, plus B, capital US. And U should also be a vector. So now this is a Laplace transform of the state equation. And we need to rearrange the terms to find XS. That is shown by this step. One thing you need to pay attention to when you rearrange the terms is that you need to consider adding the identity matrix, because matrix operations can only take place when you have compatible dimensions of matrices. Another thing you need to pay attention to is you can't do a division by a matrix. Matrix divisions can only be done through left multiply or right multiply of the inverse of a matrix. That's why we have this matrix inversion here. Once we get XS, we can take the inverse Laplace transform to find xt. The multiplication here in the S domain, it should be the convolution in the time domain. Therefore, we get xt as this. Matrix exponential function is what we are going to call here the state transition matrix. The definition of this matrix exponential function is given by this infinite power series. This slide shows you the function of state transition matrix. After we define the state transition matrix to be the matrix exponential function, we can rewrite xt using the state transition matrix phi t. If the system has a zero input, which means it is an unforced system, ut equals 0, the state xt can be simplified to be this. So xt is simply equal to phi t times x naught. Now you can see the role played by the state transition matrix. It translates the initial state of a control system into the current state, xt. If we expand the state transition matrix, it is a n by n matrix. With the state transition matrix, we can write the full solution to the state space representation. It is expressed by these two equations. In the description of the system of YT, we can easily see two terms. The first term is the initial condition term. This initial condition term represents the natural response of the system because this is a response when the system has no external input. And the second term in the expression of YT shows a forced response because this term represents how the system responds to an external input U of t. How do we derive a state variable model of a given physical control system? I'm going to show you through a couple of examples. The first example we see here is an RLC circuit. We want to model the voltage Vt of this circuit. The input is a voltage source. The way we write a state variable model is by applying our knowledge of a circuit, which is supported by KCL or KVL. So by applying fundamental network laws, we obtain these equations. Vt is equal to L multiplied by DIL dt. And the second equation is just the node equation using KCL. So how do we relate this to a state space representation? The relationship is given by defining state variables. How do we define state variables for a given physical control system? We need to remember that state variables represent the characteristics of a physical control system. Therefore, we need to choose those variables that are representative of the dynamic behavior of the system. In this case, it is meaningful to define x1t to be IT, which is the current flowing through the inductor. We also want to define x2t to be the voltage across the resistor R2. And this Vt is also the output. Once we have done that, we can rewrite the two differential equations we derived earlier into a state space representation. And this is shown by the matrices A, B, C, and D. In this process, we need to recognize this first order derivative of IT is simply x dot 1t. And this one is x2t. This is x2 dot t. This is x1t. This is x2t. To write the state space representation in matrix form, you need to be familiar with basic matrix operations. Since this is a second order system, matrix A should be a 2 by 2 matrix. Therefore, it should have 4 elements. The first row of matrix A is derived from the first equation shown on the slide. The second row of matrix A is derived from the second equation shown on the slide. Same for matrix B. Matrix A is derived from the output equation. The output equation is very easy for this example because the output y of t is simply the second state variable. Therefore, matrix C should be a row vector and it has 2 elements in it. Matrix D is 0 because we don't have a direct relation between the input and output. Now let's look at another example. This example is also an RLC circuit. Again, we need to choose state variables in a meaningful way. And the 2 state variables we choose for this RLC circuit are VCT and ILT. Now let's derive the state variable model for this RLC circuit. Because this circuit has a current source, UT, we can use KCL to write the node equation. UT is equal to IL plus C, the capacitance, dVC dt. We can also write another equation. VC is equal to L dIL dt plus R multiplied by IL. This is Ohm's law. Once we've written these 2 equations, we can rewrite them into the required format. And what is the required format? The required format for a state space representation is x dot t tilde is equal to a xt plus b ut yt equals c xt plus v ut. And the first equation we call state equation, the second equation we call output equation. So by looking at the features of this state space representation, we can say that on the left-hand side of the state equation, you need the first-order derivative of the state variables. And on the right-hand side of the SE, you need a linear relationship between the first-order derivative of state variables and the state variables themselves, and the relationship of the first-order derivative of state variables and the input. You need to recognize IL is simply x2, and dVC, this is C, dVC dt is x1 dot. dIL dt, this is L. dIL dt is x2 dot. IL is x2. VC is x1. I've omitted t for simplicity, so all of this should be understood as a function of t. And once we recognized all this, it's not difficult to write something like this. And by writing it in this form, it satisfies the requirement of a state space representation. The first two equations, x1 dot and x2 dot, give you the state equation. The last equation, v naught, gives you the output equation. And if you want to write this into the matrix form, it should be easy enough. So matrix A is equal to, again, is 2 by 2, 0, -1 on C, 1 on L, -R over L. So this is your matrix A, and matrix B should be equal to 1 on C and 0. Because in x2 dot t, there is no appearance of u of t. That's why you have a 0 as the second element of the vector B. And matrix C comes from the output equation. And because in your OE equation, x1 hasn't appeared, the first element of C should be a 0, and the second element of C is R. And D is 0, because we don't see a direct relationship between the input ut and the output v naught. For this same RLC circuit, if we define a different set of state variables, we will obtain a different state space representation. So this time, if we define the state variables to be x1 hat and x2 hat like this, obviously we will get a different state space representation. So for these two different state space representations, they actually correspond to the same system, and the transfer function of the system can be obtained like this. Although we have obtained two different state space representations, they belong to the same system. If I generalize what I have just said, I can make the following statement. For a given transfer function representing the input-output relationship of a physical control system, theoretically speaking, there exist infinitely many state variable models, of which describe the same system. The reason we have so many state variable models corresponding to the same system is because we can define different state variables. Once we have a different set of state variables, the state space representation will be different. Now we summarize what we have learned so far. We know that state variables of a physical control system represent the characteristics of the system. State variables don't have to be physically measurable or observable quantities. However, it is convenient to choose readily measurable quantities to be the state variables. We have seen from the example that state variables are not a unique set. We can choose different variables to be state variables as long as they characterize the behavior of a system. The concept of state variables is not only limited to physical systems. It can be extended to financial systems or even social systems.